Friends, it's a pleasure to have Christian Maes here. Christian is a physicist with a broad interest in physics. And I think, as you will find out today, he likes to rock the boat. So I'm glad to see some astrophysicists in the audience. Christian?
Okay, well, thank you very much for having me here. As I said already, it's a very nice experience for me to be here. I like it a lot. Here I want to speak about somewhat an intersection of problems related to non-equilibrium physics and cosmology. Usually I am doing statistical mechanics and I'm doing simple things. But somehow recently I got more and more interested in some problems, at least, of astrophysics, astronomy, and cosmology. And somehow one of the joys was that I discovered that probably there are many things that we could also think about. After all, the thermal history of the universe has a lot of kinetic theory, has a lot of thermodynamics, but also more and more because of cosmology becoming a data-driven precision science, it becomes more and more possible to check fluctuations, and fluctuations, that's about statistical mechanics for a large part. So in a way, statistical mechanics has been involved in biophysics, in biology, or in information theory, or in various aspects of condensed matter theory. I think that I find it very useful, perhaps, certainly for the moment interesting for me to make some excursions into astrophysics and cosmology and see what happens. So that thing that I want to discuss today is a paper which is not published, who knows, but it is about a work that we are finishing right now. The paper is written actually, and has to do with a problem, let me call it a problem, in observations that have been recently reported in NASA missions concerning the cosmic background. So that will be clear, I hope, in a moment. But somewhat in a broader sense, I would like to discuss about two questions, and which are complementary in ways you will see. The first thing has to do with the origin of so-called kappa distributions in solar plasma. So, there are these plasmas around as the result of solar emissions, let's say. So there are many charged particles, electrons, which are living together with the electromagnetic field, with photons, making a very complicated plasma. And various missions since a long time already have been measuring velocity distributions of the charged particles, of the electrons, and found that they are superthermal tails. Namely, they have power law decay instead of exponential or Gaussian type of decay for Maxwellian. Another question is, as I said, complementary, is that one has found something which is called nowadays the space roar. Some of our colleagues in astrophysics and cosmology are very good in inventing the names related to a problem. And the space roar is this roaring sound that is emitted in the cosmic background, and which show, as far as we believe, real in the sense, nothing related to experimental errors, real low frequency deviations with respect to the Planck law. So these are the two questions I would like to discuss. They are sufficiently simple questions of nature, I believe. Okay, so the Q1 is the first question, is a little bit more about this kappa distribution. So in this picture here, if you can see it, it's just a picture with some colors. That if you're looking at the space plasma, as I was saying, so these ions interacting with the electromagnetic field, it seems repeatedly, it has been observed and also studied, of course, a lot, how we can understand the power law decay in the stationary non-equilibrium. That is discussed in books and articles, and many things have been applied. It has been applied to understand certain instabilities or stabilization effects. This I will not discuss. I will just use it like a step going to the space roar. So the second question indeed is about the space roar. As I said, there are these NASA missions starting, I believe, already in 2006, and has been going on maybe for 10 years, where this mission is called Arcade or Arcade 2, where they have been seeing starting below 3 gigahertz deviations from the Planck law. And obviously, they have been checking their instrument maybe 2 times, 3 times. Obviously, they have also been very precise in subtracting effects, low noise effects coming from other sources, possibly galactic or other sources in the universe. But still, it seems that after all these careful checks and balances, that there remains an abundance of low energy photons in what usually was called, the Planck distribution, which was emitted a long time ago and which we see as a kind of remnant of the early universe. In particular, if you are looking at such a plot here, you see the frequency in the horizontal axis, and the vertical axis is the associated Planck temperature. You can look at, you apply the Planck law, and you see what would be the temperature corresponding to the observations, and there you see this deviation and this abundance of many more low frequency photons starting at gigahertz of order 1. For the rest, the Planck law is very well satisfied all the way, say from 10 on. It's a perfect fit. Okay, so that is the main topic that I want to discuss, but before we come to that, as I said, let's us first go to this issue of Maxwell versus non-Maxwell in classical statistical physics. So since this is a colloquium, perhaps I can also broaden a little bit the issue here and remind you of a quote of Boltzmann, which I think is a bit mysterious, but also in a way very deep, and I will not read it to you, you can read it yourself, but it basically says that the Maxwell distribution is in no way special. And then it is characterized by the fact that by far the largest possible number of velocity distributions are Maxwellian. I think I can imagine that if you read that as a student or somebody who is not used to thermodynamic statistical physics, that may sound a bit strange. So what Boltzmann is saying in that quote is that basically, there is only one distribution of velocities, and that's Maxwellian. That's based on, this is not quite what Boltzmann is saying in that quote so long ago, but he emphasizes a point that somehow, let me summarize it in the following way. Boltzmann is saying in that quote that if you see the Maxwell distribution, that's like seeing something that is normal, that's something that is typical. Don't be surprised if you see Maxwellian distribution. And that, of course, has much to do with the statistical interpretation of equilibrium, which amounts to saying that the equilibrium condition is the one which is the most typical in the sense of counting the microscopic states for a given macroscopic condition. So if you specify the energy, the number of particles maybe, the volume, then without any special things, you would see equilibrium and you would see the velocity distribution as described by Maxwell. That is what we were, this is the lesson already more than 100 years old that Boltzmann has been teaching us. So in particular, if you take your first class in statistical mechanics, you probably do some exercise like understanding that for an ideal gas, this is the computation that Boltzmann was doing, that it is basically a law of large numbers as we see it in probability theory, to understand that if you're fixing the energy there, just in terms of the temperature, which is just a way to relate monatomic ideal gas to energy, and you're asking for the fraction of particles, n particles that have a velocity which is very close to a given u, that fraction is by typicality, by counting, equal to the Maxwell distribution. So a bit of a puzzle sometimes why this u squared appears. This is just the energy, right? If the kinetic energy would be u to the 4th power, it would be u to the 4th. So it is not the law of errors. It's not the central limit theorem at all. This is, the Gaussian does not appear here because of a law of error of central limit theorem. It's because of the law of large numbers that it appears. Okay, all of that basically, well, I think it's still interesting and useful to know this and to remember that. But just to say that statically, it's just typical what you expect, and dynamical understanding for a dilute gas, of course, you can use your preferred dynamics, like given in the Boltzmann equation for a dilute gas, or if you have a tagged particle in a dilute environment, you can use the appropriate Fokker-Planck description, Leuven dynamics, to all understand how via detailed balance you approach and you see the exponential distribution as given in the Maxwellian. And indeed, it has, of course, also been tested in experiments, or in fact rather late. No, this is 1927 only when they. And in fact, the method they are using, the method that is used to measure there the Maxwellian 27 is basically the same method conceptually, of course, much more sophisticated, but basically the same method to to measure the velocities in a space plasma. It's basically by selection. So you just look at, if you turn, like these fans are like the typical measurements of velocity distributions, because particles have to pass by at a certain velocity. Okay, so now this to say that if we see a non-Maxwellian, it requires an explanation. Of course, you could say, well, if it is non-equilibrium, anything happens, anything can go, so why would we be surprised by non-Maxwellians? That is correct, but maybe one can be a little bit more ambitious and try to see whether this specific non-Maxwellian that you see in space plasma can be derived, can be understood physically by a mechanism. And as I said, plasma physicists in literature have been describing it, for me, in complicated ways, not always understandable, how one could understand that, but I will give an explanation which is, on the one hand, I believe, at least for me, simpler, and secondly, it is a good step, as I was saying, to understand, perhaps speculatively, the space law. So here we go. So the key ingredient will be the notion of stochastic acceleration, that I also will have to describe what I mean by that. I see. Before getting to the more specifics, but this is the time, okay. So before I get to the more specifics, let me remind you of another thing which is quite trivial, but important. And that is that if you go away from detailed balance, from equilibrium, then the distribution, the occupations, the population, the distribution, the stationary distribution, start to depend on aspects of your dynamics that perhaps were not so relevant when you were in detailed balance. I will repeat that point, so I will repeat it immediately already now. I'm saying that if you're looking at the dynamics, it has often a lot of parameters, kinetic parameters, like the friction coefficient and the Leuven dynamics. But if you're looking at the stationary distribution in equilibrium, in detail value, you don't see even this friction coefficient, you just see the thermodynamic temperature. This kinetic information is somehow gone when you're detail balance. In non-equilibrium, that does not need to be true. This kinetic information will matter. That, on the one hand, is a blessing, because it means that you can also control the non-equilibrium population. Or, to say it a bit more poetic, nature can make use, it's not so poetic, but nature can make use of these kinetic effects to tune the non-equilibrium in a way which is most useful. Like the example in biophysics that I particularly like is the one of the kinetic proofreading, which was discovered by Hopfield already some time ago, where the problem was that the expression of proteins certainly does not follow a Maxwell or a Boltzmann distribution. We would not be here if it would follow the same kind of statistics. There must be a certain abundance of certain things that we really need for well functioning. And how Nietzsche does that? Well, by going, of course, to non-equilibrium. We are all, in a way, non-equilibrium people. And moreover, to make use of this kinetic aspect to make a biological error coding efficient. So that's just an example where you see how you can change the statistics away from Maxwellian or away from Maxwell-Boltzmann distribution by non-equilibrium, but in a controlled way. Okay, and it doesn't need to be by driving. So I'm not going perhaps to emphasize that point once more, but perhaps if you happen to be familiar with processes which are described by jump rates. So you imagine that you have on a certain level of description states x and y, and the transition happens at a certain rate, kxy, like in Markov jump processes, chemical kinetics, these kind of contexts. Then one often writes this in, well, let me call it an Arrhenius type of way, where you have a prefactor which is symmetric, and then as a parameterization one writes in the exponential something which is anti-symmetric in the transition. Of course you can always write it like that, at least if it is non-zero. But if you have detailed balance, so detailed balance is like a dynamical condition for ensuring equilibrium. It is basically referring to time reversal invariance, so reversibility of an underlying, possibly closed mechanical system, Hamiltonian, which is time reversal invariant. If you look at the coarse-grained description, you inherit detailed balance. It's a deep thought that basically goes back to Onsager. To understand that time reversal symmetry in the mechanical world, if you coarse grain, you integrate all degrees of freedom and you come to such a description, much more coarse grained. If nothing bad happens in terms of frustrating boundary conditions or non-conservative forces, that you inherit in your chemical jump processes is detailed balance, and the detailed balance in mathematics means that this Sxy, this antisymmetric factor, is a difference of a potential, a difference of an energy, you could say. And in fact, if it is true, then the Boltzmann distribution is the stationary distribution, and all is, it only depends then on the V, and this A are irrelevant. That's what I said, that the kinetics becomes to some extent, to some big extent, irrelevant for the stationary distribution, as the stationary distribution is just the exponential of minus the energy, or the Gibbs free energy, whatever, while the kinetics of the A is forgotten. It's not necessary to know about that. Okay. So that is, I will not give that application, but it's just another application of population inversion that you can do in lasers by adding a time symmetric component. It's a principle that is used in many ways. Okay, but now let us go back to question 1 and start there. And so the question I remind you is, can we get sufficiently simple, in the sense of statistical mechanics? I don't know whether everybody here knows people who work in statistical mechanics, but I will tell you a secret if you don't know them. They are rather opportunistic people, in the sense that they like to work with simple models, and they are not always delving into the most complicated, a priori, ab initio calculations, or, of course they are above that. They think about what is the model that captures the essence of the physics, and then sometimes when really asked, they will say something like universality, which is the type of motivation that brings them to say, well, we believe in it, that it is. It's sort of fun to say that it is real, something like that. So I will take that nice kind of spirit in this room to be an opportunistic statistical mechanics, and I will not worry too much about many details, but I try to believe in a kind of principle that gives us what we see. Right? So from here on, do not expect very complicated things at all. Okay, so what I believe are the two ingredients. By the way, this is not completely original, no? What I'm going to say, maybe the way I present it is a bit special, I don't know, but if you read all these texts, books, papers, you basically enter into the same scheme. So the main ingredients are two. One is the Coulomb scattering. So you have to imagine that you have charged particles scattering off each other. So you have to look at the Rutherford formula for the scattering. And then you will find that the Rutherford scattering cross-section goes like 1 over the energy squared. That is typical, that's the Rutherford formula. So the energy 1 over the energy squared, this means that it is, if you have very high energetic particles, they are scattered very, almost not, right? Because it goes like 1 over the velocity to the fourth power. This is this fourth power that you will have to remember. And then on the other hand, we also have something that we would like to call a turbulent plasma. Of course, turbulent plasma, that's just a word. I could even make it more obscure by saying a chaotic plasma. But you could imagine that this particle, this electron, is visiting very places where there is this, electromagnetic field changing with space and time, and it will, by that mechanism, going very quickly, it will feel a stochastic acceleration of which the diffusivity will be of order 1 over this velocity. I will explain it a little bit better in what is coming. So the setup is typically for a non-equilibrium environment. So you should imagine I have tagged my particle, that's this gray balloon there. It's just my tagging of a particle, by looking at some particle, sometimes it grows. With people it also happens. And then this particle is in contact with passive particles, the blue ones, other like us. And then maybe also non-equilibrium degrees of freedom, which I have made with the red arrows. So to say that there are also particles there which are maybe driven by time-dependent forces or by non-conservative forces. So it's just a cartoon of the situation that we should have in mind. And as I said, the two ingredients will be, on the one hand, the interaction in the terms of the scattering, which is basically an equilibrium dynamics, and on the other hand, being exposed to this non-equilibrium aspect. Okay, so maybe let me start with the diffusive or stochastic acceleration. In fact, this goes back a long time, this mechanism, and it's from the 1920s. There is something called Taylor dispersion. And Taylor discovered theoretically and also experimentally that if you are in a flow, if you have a particle in a flow, that there is an enhancement of diffusion. And what is the mechanism of that? So here is a mechanism that is a non-equilibrium mechanism, and yet it's not by driving. When we think about non-equilibrium, it's often that we think there are currents that we impose by making gradients in temperature or gradients in chemical potential, or maybe you have a fixed electric field or vortices that you impose by all kinds of ways, and that way you get a current. But that's not quite, you will get a current, all right, but that's not quite what you should have in mind. It's not like mass transport that is being done, because the net force will be zero. That's the basis of stochastic acceleration. So think about this calculation. So it's a little calculation which I think, if you have not seen it, is maybe instructive. So you look for a very small time epsilon, and you look at, say, the velocity of the ith electron, and you look at how the momentum is changing over a small time. And how it does that, well, I here took the simple case where I have a force on that particle which just depends on the position, where it comes. And since this epsilon is very small, I just take velocity. This v is really v0. So it has initial velocity, and it is in position vs over this small time interval 0 epsilon. But now imagine indeed, okay, so now make a change of variables. I hope it's correct. But now imagine indeed that you have, okay, something like internal dispersion that, first of all, imagine that this force field is non-conservative. So in other words, you do not have that if you integrate this force, that it just is a difference of potentials. Because if a force would be like a potential, derived from a potential, the work done, would be independent of the path, and you would just have nothing which is time extensive. But here it remains time extensive because of the non-equilibrium nature assumed of that force. And moreover, we assume also that there is sufficient reason to apply the central limit theorem. I mean, poor man's choice. I mean, the first thing you do is to apply the central limit theorem because, this particle comes everywhere. This force is turbulent, random, sometimes in this direction, sometimes in the other direction. So it's zero on average, but there is a first order which is Gaussian. And that is the stochastic acceleration in the sense that you keep that the change in momentum is indeed of order square root of epsilon times the Gaussian, where this 1 over v is this diffusivity that you gain. So depending on the velocity, this v is the v0 at time 0, you get an extra diffusion where the amplitude is like 1 over v. That is the calculation which is goes back to Taylor and which is basically telling us how a random force field, non-equilibrium, not necessarily induces something mass transport, but you get velocity transport here, in the sense that you get an extra acceleration, but which is diffusive. Okay, so that is an ingredient that I'm now using, and the using is as follows. I hope it's readable. It's a bit of a long equation, but let me guide you through it. So rho would be the velocity distribution. So rho is a function of v and t. So v is the three-dimensional velocity vector. It depends on time, and so rho of vt would be the probability distribution. Say, if you make a histogram of your measurements of how the velocity is changing, that would be the velocity distribution, and it changes in time. So here is, of course, an approximation in many ways that we are thinking of this stacked particle described by a Fokker-Planck equation. I mean, that need not be, and this requires a kind of weak coupling limit, dilute situation, all kinds of conditions which seem to be, to a great extent, satisfied actually in these space plasmas. And it's certainly an approximation which will tell us that interactions or density is not so important, apart from the ones that I mentioned. Okay, so here is the first term, and this first term I would like to, if you recognize that, so there is here a derivative with respect to the velocity, say, the speed, this is the speed. So this is a first derivative, and then follows a second derivative. So this part is the so-called equilibrium or detailed balance Fokker-Planck part to get Maxwellians. So I have here a friction, the damping coefficient, which goes like 1 over v cubed, which is exactly what I was telling you when I was speaking about the cross-section. The cross-section for Rutherford scattering is 1 over v to the fourth. So that means that the damping will be like 1 over v to the cube, because you have to multiply with an extra v. So that is the order of magnitude of this gamma. And then you have the usual kind of square bracket here. And note what I said, that here the solution, if you put that equal to 0, I mean, forget about this for the moment. If that is equal to 0, you're stationary, obviously. And the solution of that is the Maxwellian. And note that it does not depend on the gamma. That's what I said, it doesn't depend on the kinetics. This damping coefficient, you can give it whatever it does, doesn't matter. You get just the Maxwellian by solving, by putting that equal to 0. So rho, which is exponential of mv squared over 2kt, solves that equation. Right? I hope you're not worried about the volume part in the velocity, which gives you, of course, this other v4 pi v squared. I mean, that is. I mean, somehow you see this remnants in this, the way that is written, it's just, three-dimensional Fokker-Planck equation. So you have here this 1 over v squared and the v squared, which are related to 3 dimensions. Okay, but so the main message is that this localization, you see, I call this localization because the high velocities, they scatter not. Right? They are like invisible. I mean, the high velocity electrons, they just and find no things in their way. But in equilibrium, it doesn't matter. All right. But now I'm adding here something, and what I'm adding is again a diffusion. You see, it's again a second derivative, and again these v squared have to do with three-dimensional counting. But now I have added here this 1 over v, which is the stochastic acceleration. So I just add this 1 over v, and I'm finished. No, it's done. So this is the statistical mechanics solution of the kappa distribution, because now I have motivated, I have here 1 over v cubed, here I have 1 over v. Now I put this equal to 0, and I look at what are the solutions for this rho, and I find the kappa distribution.
How is kappa image as a constant?
Okay. Okay, so the kappa depends on various constants, of course, having to do with prefactors that have appearing like this kt over m, but also prefactors that I have not been writing here, or prefixes that I have not been writing here. So I have not been careful enough to spell out what is kappa, but it fits if you do it more carefully, and more importantly, you see this is absolutely easy calculation work, because since you're working on the level of isotropic space plasmas, so you can go to the speed really, which is a one-dimensional variable, so you're dealing just with differential equations with one real variable, and you can solve these things, you can find a stationary distribution. I will not bother you with that, but it's just one dimension, you know, it's just the speed. And you just plug in the values that are the physical values in your equation, and you end up with a stationary velocity distribution. In fact, you can also find stress exponentials if you would have other frictions. You know, if this gamma v would be not like 1 over v cubed, but others, then you would find other exponents. You would have a stress exponentials like you have in granular media. But if the eta is equal to 1, which is the case corresponding to our 1 over v and here 1 over v cubed, you see here you get then v to the 4th power, or v squared, sorry, which means eta equal 1. So you don't have the stretched exponential, but you just have this power law decay with kappa. And the kappa and theta I have not spelled out in this calculation. Okay, so this was a warm-up, so then you have all these, okay, you can go to the energy and the suprathermal tails that appear at high velocity, which is just my introduction for saying how two things have leading to the power law. One is the localization, which is just a big word for saying, look, Rutherford scattering, high velocity just passed through, localization. And on the other hand, stochastic acceleration, which means, yeah, you know, this electromagnetic field is changing rapidly in space and time and gives rise, as for Taylor dispersion, to another diffusivity, which is of order 1 over v, by abstract nonsense really coming from central limit theorem. And that is enough to understand on the level of a Fokker-Planck description how you get a kappa distribution in these astrophysics space plasmas, which in fact fit the data experimentally. So that is fine. And having seen such a success, if I can call it like that, then you say, let us be more ambitious. So you turn around the corner, and then you suddenly are in a collaboration with many people, astrophysicists, people who really know plasmas, and we tried in that paper then to understand also the origin not of non-Maxwellians but of non-Planckians. You see, in a way the step is not so big, because a Planckian, I don't know whether that word exists and whether it shows sufficient respect to Max Planck, but okay, Maxwell has a Maxwellian, Planck must have a Planckian, it seems, so there must also be a non-Planckian. So to understand the non-Planckian is a bit similar to the non-Maxwellian in many ways, because what the Bose distribution is gives the Planckian, and just like the classical Maxwell distribution appears for classical particles. So it's a bit a similar game, but you just play it a bit on the quantum level. All right, so these are co-authors for a paper which is being finished. Now I have to warn you, perhaps. Here the warning is a bit that what I'm going to say is certainly not standard accepted, I think. Well, you will see why. Okay, now the first thing you would like to understand is what is really the natural dynamics. You know, before we had the Fokker-Planck equation, and I said this is like a poor man's, not only poor man, there is a statistical mechanical way to understand the origin of Maxwellians, not dynamically. So the first thing you want to understand is the Planckians. How do you get them dynamically? In fact, if you look in the standard textbooks of statistical mechanics, I have done that, you do not find that information. And if people are teaching advanced course in statistical physics, they are not giving that. You know, what is the dynamics? What is the simplest dynamics, so to speak, which gives rise to Planckians? Anyway, it exists, and it is more or less hidden in the books of cosmology and astrophysics, and it's called the Kompaneets equation. Kompaneets equation is old, not so old as Fokker-Planck, but still respectfully old. And there it is plotted. And if you look at it, it has a bit of the same structure as Fokker-Planck. This is for the photon number n. So this n now is a number, or it's a real number, which depends on time, tau, and on frequency. So nu is almost like a v, but it's a nu, is the frequency. So it counts the number of photons with a certain frequency nu as it evolves in time. And it has a second derivative. You see these deltas here, these are second derivatives. And then there's of course the first derivative. And here we have the constant of Planck. Here we have a temperature, I call it the electron temperature and Boltzmann's constant. And again, if you're looking at just the bracket has been curling up a bit because it's quantum. No, I should have changed that notation. In quantum, you write square brackets, I think. In classical, you write curly brackets. But it's the same idea. So if you put that equal to 0, this thing, actually it's a square bracket which is equal to 0, sorry, then you just find the Bose-Einstein formula for the density. In fact, the C is equal to 0 for photons for chemical potential. But it's basically, again, the same thing. You don't worry about the nu to the fourth. This is the kinetics. All right? So you see nu to the fourth, but it's really nu to it's nu squared, which is written there. I mean, you see there is this v squared. The nu squareds again come, even though nu is like a scalar, but it's again coming from 3 dimensions. Maybe because you remember that if you have to count energies, you have to look at the wave number in 3 dimensions. You have to count how big this is, and that's the nu square. So basically, if you wish, not if you wish, but what was the gamma before? You remember the friction is now the nu squared. So, in other words, now you have localization at low frequency, which is not so strange after all, because after all, submarines communicate with extremely low frequency, right? And the reason why they do is that because if I speak with a sufficiently low voice, you will even hear me better.
You get Planck with the chemical potential.
Yes, in general, in the Kompaneets equation, you get the general chemical potential. Yes. But you can, then we just put it equal to 0. It's like an integration constant, basically.
The physical reason for this. The physical reason is that this equation is derived from Compton and inverse Compton scattering. In Compton scattering, the density of the number of photons is conserved. So you can, if you inject energy into the system, then you cannot reach a blackbody at the temperature.
It's a new distortion.
That is, the C is the new distortion. But in Kompaneets equation, if you add other terms like from free emission and absorption and from double Compton scattering, then you reach an equilibrium in C to 0. That is the only solution to it.
Yes, thank you. I think I read that, but I wouldn't be able to say it. Yeah, actually, maybe it is worth, of course, to repeat what you said, and that is that, maybe before so the general way this is derived, this is not necessarily related to the blackbody radiation, this is more like plasma physics. The general way this is derived, like many things in our life, is by Boltzmann equation. So you start from a Boltzmann equation jointly for degrees of freedom like photons and maybe electrons, and then you have to make various approximations, non-relativistic approximations, high enough temperature, various approximations to integrate out the electrons and to remain with the electrons. But of course, in the Boltzmann equation, there is all kinds of mechanisms that you can put in, all kinds of scattering mechanisms. So there's Bremsstrahlung, photon scattering, all higher order, all kinds of things that are important. So what we did, I repeat, we are just statistical mechanicians, we just wanted to have the simplest mechanism to deal with it. In fact, this may be an important point because it could be very much possible that it's something I don't like, but still, sometimes things are happening that I don't like. It could be that this problem of the space law, which is the low frequency distortion of the Planck law, could be because there are all kinds of mechanisms that that people have neglected somehow. I mean, that in fact that there is no Planckian law, but there are all kinds of further higher order scattering mechanisms in the primordial plasma that have given rise to this. The reason why I don't like that, or why I don't believe it, is that the same thing as Boltzmann's quote. Then you can make very complicated things. But if you have time reversal invariance, you get Planck. You know, there was the beginning quote of Boltzmann that says, you know, Maxwell is everywhere, don't look. I mean, Maxwell is there. So the same thing is true about Planck. It's again a counting argument to get Planck. So you can invent all kinds of complicated mechanisms, but as long as you are, you know, on the level of equilibrium thermodynamics, it's just Planck that you find.
Can I make a point here?
Please.
See, the point is it's actually easier to get equilibrium at low frequency than at high frequency.
Oh, I'm very
because
happy.
of free absorption. The free absorption is one of those processes which works much more efficiently at low frequencies than at high frequencies. So typically if you inject energy into the system, you equilibrate faster at low energy. So this is even a bigger conundrum actually that you are seeing in excess.
Okay.
Because if you were to believe in the microscopic physical processes, Compton, inverse Compton, free emission absorption, double Compton scattering, and its inverse, then you should get equilibrium at low frequency much more easily than at high frequencies. At higher in the frequency tape, you would probably expect like some deviation.
Mm-hmm.
What you said.
Yes, yes,
Because
yes.
there the processes are less efficient.
But I thought the data shows deviation at low frequency.
So that's what I'm trying to say. So that's a bigger.
Keeping the data aside and the mu distortion itself does have a spectral shape.
That's right.
Yes,
That's
it goes to zero at very low frequencies.
It goes to zero at low frequencies for this reason.
And given all the data, there are already limits on mu distortion at the level of 10 minus 5 or 6.
Yeah, so of course I also have to add that the plots I showed, there was not extremely low frequency, of course, no? And you expect that it goes to zero, but there is a peak at low frequency. So when I speak about low frequency, it's a bit different from the suprathermal tails in the kappa distribution, where it's really all the way. Here I'm looking at a window of low frequency.
So mu distortion peaks at about a gigahertz.
Mu distortion, I
As
think,
in
yeah, it does.
indication.
Yeah, that is where it typically does.
Yeah, and then it goes to zero.
No, but that data you're quoting is probably not at that frequency, right? You're quoting fires data.
Yeah.
No, the CMD measurements exist down to 400 megahertz.
Yes.
And
But
there
there,
is no
the
deviation.
precision is not that high, right?
It becomes, yeah, well, as you see,
For the CMD. For the CMD, there is precision up to 400 megahertz. Kelvin.
Then what is arcade is
This has
showing?
nothing to do with CMD.
Still, so do you think it is coming from galaxy?
Yeah.
So are you speaking about the arcade mission?
Yes.
And so you're saying,
So
sorry.
the arcade itself, so you have this plot at the beginning.
Yes.
Which showed a certain excess.
Yes.
So if you look at how they have got those points,
Yes.
what they have done is to take a map of the sky, a radius map, and then they assume that we live in a galaxy which is a slab, and nothing more than a slab, which means that you have a cosecant variation in intensity.
Maybe I even have a picture of that. Let me check. No, I don't have a picture. I thought I had a picture.
So they assume that it's a slab model. They then fit for a cosecant law, and then they subtract that out, which is subtracting out a slab model. Then if you look at a picture of what is left, there's all the structure that is there in the sky, the filaments and everything. Then an average of all that is what is plotted. So it represents the average of what doesn't fit a slab model. It has nothing to do with CMD.
So if that is true, then this talk is not very relevant anymore, right?
Yeah.
So what I thought, and we thought, that the data that they got, it tells us something about CMD.
No, they don't claim it.
I see. That is not what I heard or read. I see. So then I'm very sorry, of
But there is
course.
one observation. This suggests it may have something to do with that is edges. Edges is right.
Yeah, but that's a different.
That's
Oh,
right.
yeah, the 21 centimeter line in hydrogen.
Then it is coming from far.
So I thought there were three independent, more or less, sources. There is the arcade, there is the edges, and there is the what's called the philas, probably, no? Philia or
Philas.
Yes. And I thought, and that's what I read also in all these papers, is that it's a bit of a problem. How can that arise as it is supposed to represent the CMB?
The virus is 60 gigahertz and above. This is not in the virus frequency range.
I mean, there are. I mean, there's an accumulation of all these data. No, that. Okay. So maybe let me continue. You know, but sorry, the point is taken. Okay. So So I was telling you that this comes from a Boltzmann equation. Of course, you have to introduce this cross-section there, and you get this Kompaneets equation in the simplest case. So now, what I read, what I thought, maybe incorrectly so, is that arcade, after subtracting and after correcting all kinds of errors and after thinking about it very deeply, they do see a residual emission lower than 3 gigahertz. That is what you're saying is not correct, right?
They see an excess beyond what model they use.
Well, beyond, I say, it's not. They don't see the Planck distribution, and they believe they see the CMB.
No, not CMB. They have an excess which doesn't fit the models that they have.
It doesn't fit the models that they have. Okay, okay. So I'm already happy it doesn't fit the models they have. But okay. So they see a residual emission in the low frequency range up to 3 gigahertz. Okay.
But it only means that their models are inadequate.
Probably yes. All right. So now I want to do the following now. I want to say that I would like to repeat this thing about kappa distribution. You have to understand that in this kappa distribution you have also the electrons in contact with electromagnetic field, similar to the primordial plasma. So if these electrons are not in equilibrium, they are starting with this kappa distribution, then maybe the photons are also not in equilibrium. So in that sense, this is what I was saying is like a complementary issues. On the one hand, the electron degrees of freedom, and on the other hand, the electromagnetic field. But more specifically, what we do is the following. You see, here again you have the simplistic Kompaneets equation, where you have the usual diffusion with the nu squared, and the terms which are sources here. And then what we are adding here is the same thing as we are adding for the Maxwell distribution, for getting the non-Maxwellian. And we are again adding not 1 over v, but 1 over nu. The reason is against stochastic acceleration, but now in frequency space. So the argument that I gave about the central limit theorem is exactly the same for frequency, because the momentum transfer is now on the level of h nu, which is being transported in this contour scattering. So you get this 1 over nu, and what do you see? So I think the mathematics is trivial, right? So you have the combination, the nu to the 4th, or the nu squared, really, which used to be the v to the minus 3 for the damping in the non-Maxwellian. Here you had the 1 over v, and now it is the 1 over nu. And the result of this thing is, well, you just plug that in. So you get this extra combination like we had it in the non-Maxwellian. So this is all trivial mathematics. And what you have is the same plot, except that now we have, if you compute the stationary distribution by just adding this 1 over nu, just the same principle we use to get the kappa distribution, we get, well, I would think from what the people compute numeric, the fitting that they are doing, putting the data together with a solution of the Planck Kompaneets equation, they get a very good fit to the data of arcade. So, yes. I haven't, I said many things I have not included.
That's the one that creates equilibrium.
That creates what, sorry?
The equilibrium at low frequency.
But I think, so, okay, so that could be, but what I was saying is that equilibrium is Planckian.
No,
by you mean stationarity or
in the Kompaneets equation you have written,
yes.
you have taken into account 2 physical processes, which
Yes.
is Compton and inverse Compton.
Yes.
That is Kompaneets
Yes.
equation.
Yes.
But the other term in Kompaneets equation, if you look at the full Kompaneets equation,
Yes.
there are terms from free emission and absorption and also Compton,
Yes.
double Compton
Yes,
scattering.
absolutely, much more.
So at low frequency, the dominating process for creating equilibrium is.
But do you mean equilibrium in the sense of the time reversal invariance?
Yes.
Okay, so here I think I interrupt you already. As I said, I believe in Boltzmann that whatever you make it complicated, you find Planck.
Yeah, so that's what is at low frequencies we actually know that low frequency equilibration is not created by Compton scattering, it is created by free absorption actually. Free absorption, because if you have a very, very low frequency photon.
Okay, we do know, I think I do know that there are various known deviations in low frequency, for example, with this Sunyaev-Zeldovich effect. I mean, this is all known, but that is all subtracted already, if I understand correctly, in the arcade data. So I would still think that starting with the simplest model, which gives you normally Planck distribution, that by inserting the stochastic acceleration, it seems to work very much at low frequency, and you see it's very much compatible with it. But wait, so maybe this you check in the paper, but I would like to say that there is no fitting really done here, except for the natural constants you get in the Kompaneets equation, and the stochastic acceleration is just the 1/nu you're adding. But in the same way, the constants that you put in front are the same constants that you put in front of the diffusion term. So there is no kind of jumping around with constants here. You take this equation literally as I wrote it down, and you see that there is perfect Planckian, so for the gigahertz and higher, and here you see a deviation, which does seem to follow the right trend at least, to understand the low frequency deviations. What it means, well, maybe it means nothing, but that is certainly the result of the computation that we did for the modifications of the Kompaneets equation.
Kappa distribution also have to come in there.
Yes.
Kappa distribution you have got from interactions which are Rutherford scattering, which is 1 by d.
Yes, yes.
Actually, if you look at other processes, like the way photon works, the photon equilibrates with electrons, and that is actually proportional to square the velocity, the inverse Compton scattering. So one process is going as 1 by d4, which is correct, which is not going to equilibrate. But the other process is going to be square actually, the photon. And those time scales we know are much shorter than the time scales in the early years.
But you see, again, I would like to make a point. I mean, of course, I agree with you, but still, maybe it's a statistical mechanical spirit that will play now again. You know, life is much more complicated, indeed, and there are all kinds of additional terms that you can add. But you have to look at orders of magnitude, right? And what you're interested in is how the high velocity tail is going there. And we are saying you can be very complicated in all of your scattering and in the electron-electron interactions. It doesn't matter, you will find Maxwell. That will not create no Maxwellians.
I mean, there is always non-Maxwellian under such some conditions. That, like, absolutely, it becomes relativistic.
Oh, but you
If
see,
it's highly relativistic,
yeah.
you know, no physical process.
Yes, okay, but yeah, okay, I agree.
But this is so long as it's non-relativistic.
Yeah. So that's indeed a bit like I'm not sure whether that's the. How can I sell that point of view? I don't want to sell it even, but I'm just trying to say, I guess, that there is a level of simplicity that goes to the heart of the matter. Namely, if you have detailed balance, no matter how complicated, you have Maxwellians, and now you have to understand a mechanism which quantitatively and not only qualitatively gives you the right kappa for the polar law. And I'm telling you that, look, if I just add the stochastic acceleration, it is doing it. And what I'm telling you about the space law is that if you start in the same way with the Kompaneets equation, and in the same way you're adding stochastic acceleration in the correct way, then you find this plot. And this seems to fit pretty well the data of arcade and edges. For the rest, I have nothing to say. But if this is serious, let me maybe finish. I'm almost there. So when you take that serious, and that is what I wanted, but maybe it's very much irrelevant what I'm not going to say, but let me say it. If that would be true, that is somehow something hard to accept. Why is that hard to accept? Because it would mean that in this primordial plasma, in the early universe, in this period before 300,000 years after the Big Bang, in the standard physical cosmology model, it would mean that we still didn't equilibrate. So in other words, not all processes have been on sufficiently fast scale to reach thermodynamic equilibrium. It means that we witness in the space war, we still witness aspects of non-equilibrium of the early universe. That is certainly something which is not accepted, not even thought about maybe, in the standard models of cosmology, is to introduce elements of non-equilibrium in the early universe. Because, you know, the usual textbooks and papers that I consult say, well, all these processes have time scales which are so fast that they will equilibrate just before, you know, the photons get out. And in fact, it's much faster than the expansion of the universe, and end of 2 sentences, 3 sentences at most are spent on this issue. So what we are proposing is certainly non-standard and goes in against that idea and makes room for a possibility of a non-equilibrium effect. I thought with some success, at least on a very simplified level of description. But of course, it is certainly not something which is standard, because it introduces a truly driven non-equilibrium aspect in early cosmology. I believe that if that would be true, it would open many windows of new explorations to understand the evolution of the universe, also with the eyes of non-equilibrium processes. That would be very interesting, but it could be that it is, of course, irrelevant and not true. However, so as I said, low frequency data may be evidence for non-equilibrium features, but that's very exaggerated as a conclusion. It's very much speculative. What is the origin of non-equilibrium aspects of the early universe? Well, there's only one possible origin, right? And that is that the early universe, very, very early universe, was very, very out of equilibrium. After all, it is the origin of the second law of thermodynamics that we probably find there. So what was not in equilibrium is certainly the gravitational degrees of freedom, because you had basically a homogeneous universe, at least thought in the standard model, a hot Big Bang model of the universe, but the gravitational degrees of freedom, the geometry, so to speak, the fluctuating geometry, was not in equilibrium. You know, in the sense of Boltzmann non-equilibrium, it is non-typical. It was very, very non-typical to be able to give rise to you and me. So now the question is, how do these non-equilibrium degrees of freedom gravitationally, how did they couple to light matter? How did they couple to the primordial plasma? I have no idea. First of all, because I'm not competent in this kind of physics, but I don't think that we really understand non-equilibrium gravitational physics. I don't think we understand that well. And how it couples, how it can give rise to effects of non-equilibrium in the primordial plasma, I have no idea, of course, but I think it's exciting. And if that would be possible, which I think is not so far-fetched compared to other things I read in the literature about early universe, if that would be true, it would give a natural explanation in this framework, at least, of the space roar. I mean, that's why I wanted to tell you about that. Okay, thank you very much. All right, so but I have interrupted somebody who wanted. You wanted to say something?
Yeah, so
Yes.
I just wanted to ask this: what is the strength of this stochastic forcing? Is that adjusted to get that?
Well, so the word adjust I do not like, but so it is obtained. So the one over the frequency, right? That follows from the central limit type theorem. But then the prefactors that we put in front of it are the same ones that we put in front of the diffusion. The Planckian diffusion. So here, you see, we just do. This is actually the same thing. We take here a function which goes like 1 over nu, but this we keep in the same way as we have this thing here. For some reason there is 1 over h, I don't know where it comes from. Okay. To have the right dimension, I guess. So there is no, I mean, you have to look at the paper, but there is no fiddling around. As far as I am aware of my own self fiddling, there is no fiddling around by taking a certain number there. But even, you know, I mean, it's pretty, I mean, it's pretty, at least as far as I understand, it's pretty, you see, you have to have this curve. But to understand really whether we have been honest, you have to look in the detail, I think.
Yeah, that's perfect. I have one question. Suppose you apply the same theory to phonons in a disordered solid. They would behave just like photons, and the equation, I presume, would have some relevance there.
Yeah, except that what would be the stochastic diffusion that you have in mind?
The disorder.
The disorder. So very turbulent disorder, somehow also time-dependent disorder possibly. And what is the localization that you have for photons?
Disorder would localize waves.
But it would also be the low frequency
I
localization.
guess in this theory.
Yeah, and what maybe I didn't think about it. So what phenomenon would you have in mind?
No, I'm just trying to suggest that because photons and photons have a very similar dispersion,
Yes.
maybe we can apply the theory there and look for effects.
Maybe, I don't know, it's a good suggestion. I would, yeah, a good suggestion. Thank you.
So what's the scale of the frequency at which you start seeing these?
About 3 gigahertz.
In the model, I mean, when you put in this action, this stochastic acceleration curve. So what sets the frequency?
Yeah, so basically the prefactors, the kpt over h. I mean, once more, it's a good question, but I can only tell you, I mean, there is no hidden.
This is like a universal thing that we see.
Well, that is why I dare to speak about it. I mean, otherwise, I mean, if it would just be a fitting, it would be a bit pity, no? But I dare to speak about it because I think this is remarkable that it follows quite well this data that I thought were CMB data, but maybe I don't know what they are.
Yes, I missed something with this this one at very low frequencies again supposed to
Yes.
become flat.
Yes. But actually, it would be very nice to have more data about low frequency, but that is not available or very noisy.
Intuitively, it looks a very natural framework to consider non-equilibrium statistical frames because the equilibrium description is a simple description, but to understand things and data set needs to go beyond.
Yeah, I agree, but of course there can also be an element of self-fulfilling prophet. I mean, it's not because we wish and we find it natural that it is true, but I agree that I find it very natural given the strong non-equilibrium of the gravitational degrees of freedom in the beginning of times, according to the standard model, to look at consequences of that also in light-matter interactions. Somehow these things get coupled in a way. And what remains of this non-equilibrium cannot just be, who knows, but I would hope, I would think, that it is not so strange to think that these very strong non-equilibria got coupled with the primordial plasma degrees of freedom, in particular to make sure that there is this stochastic acceleration possibility, which would then be an explanation for this phase. Whether it is true or wrong, that is certainly not decided here. That's just a speculation.
So, if there are no more questions, let's thank
Thank
Christian.
you. Thank you very much.